So there's a question. A large wooden floor is laid with strips 2 inches wide and with negligible space between strips. Uniform circular disc of diameter 2.25 inches is dropped at random on the floor. What is the probability that the disc touches 3 of the wooden strips? So I think my first reaction is I have no idea what to do, but nevertheless I can draw a picture. Let's do it. So I think strips of 2 inches wide. What does that look like? I think they would look like this. They're 2 inches wide. That's what the question is saying. All right, 2 inch, and between each of them, with negligible space between strips. So negligible space between strips means each of these lines is sort of infinitely thin. It's like a math line. Okay, and then we're going to draw a circular disc of diameter 2.25 inches. So maybe circular disc will look something like that. Okay, there we go. Nice circular disc. Wait a second. It says the diameter is 2.25 inches. So does it look like that? No, it should be wider than one of these. So let's try it again. It's going to look something like this. I don't know. There we go. 2.25 inches. It's like fatter than one of these. Okay. It's dropped on the floor at random. Okay, here is, I think, where the stuff gets hard. So we have the picture. I guess we can ask the question first. What is the probability it touches 3 wooden strips? Well, in my picture, it's touching 3 wooden strips. Is there a way we can arrange it so it is not touching 3 wooden strips? So right now, there's 1, 2, 3. Those are the 3 wooden strips. But it could be some other way, I guess. Otherwise, the probability would be 100%. Let's see. Is there a way it could go? I guess something like this. Right? And then this would be 2.25 inches out of this, right? This is 2 inches plus 2 inches. So that fits, no problem. Okay, so now it's touching 1, 2. So the question is it going to end up like this, or is it going to end up like that? And what's the probability of either? Yeah. Yes, you're exactly right. So the next thing we're going to figure out is when does it look like this and when does it look like that? And you're exactly right that depending on where it is, sort of with respect to these planks, you're going to get one answer or the other answer, and it's going to turn into exactly what you said. I think the hard part, once you have unpackaged this problem and turned it into like what's the probability that this is less than this, it's like very easy. The hard part is doing all this unpacking. Yeah, this is how I've thought about it so far. And the next thing we're going to do is exactly what you said, is figure out when is it like this, when is it like that, and turn it into a less than, greater than type of thing. Yeah, everyone with me so far? Questions, comments? Okay, so the way I would do this one, and there's many, many different ways. The first thing to notice is only the horizontal position matters. Only horizontal position matters. The vertical position does not matter. And that's because they're just planks. If you move the picture up and down, it looks exactly the same. So only the horizontal position matters. And to measure the horizontal position, let's use a random variable called x. Let's let x, capital X, random variable, be the position. And this is why it fits into our framework. This random variable x is one of these continuous random variables that can be any number, right? It can be any number, not just like 1 or 2 or 3, but like anything inside some interval. The interval is probably going to be 2 inches. But let's see what that is. Okay, this is a little underspecified right now because I've said let's let x be the position. What does that mean? X is the position. I got to make it a little bit more precise. This is the right idea, but how exactly do I define x? Anyone have an idea? What should x be? Yeah. Yeah, the number of planks over. Is that right? Oh yeah, okay. I think this is a good point. I think obviously I care in this problem about the 1, 2, 3 versus the 1, 2. But I don't think I want to put that in the random variable x. I think what I want the random variable x to do is to tell me where the thing is, and then I'll figure out some event. I'll say, I'll do some event, right? Some event that touches 2 planks. That'll be some event involving x. That'll be the same thing as x is blah, blah, blah. Blah, blah, blah. We'll figure this out when we figure out what x is, right? And so the point is, the thing we're interested in, we're going to translate it into some equation about the position. When the disk is over here, then it's touching 2 planks. When the disk is over there, then it's touching 3 planks. And then we can turn probability of 2 or 3 planks into some question about x, and then solve it that way. That's what you got to do in this question. So yeah, so we don't want x directly to be related to these. We sort of want it indirectly, and that's because the position is sort of easier to handle than 2 or 3 directly. Yeah, great point. Yeah. Oh, sure. Okay. Anyone else? Questions, comments? I guess let's go back to what I was asking, which is, let x be the position. What should x actually be? X has to be some at the end of the day, some measurement, right? Like you should be able to get your ruler out and do x. Yeah. Yes, that is very nice. So I like that. The center of the disk. This is the first thing you got to do to specify, because we're talking about a circle here. So you're talking about the left, the right, or the middle. So let's be specific. Let's see specifically, the center of the disk. And then you said the next thing you said was to where? So I measure from the center of the disk to where? Yes, this is a lovely idea. Let's write it in. So the distance from the center of the disk to the left side, to the nearest plank. Let's say the nearest line. I think that'll be clear. And so what this means is in the little picture I drew, x is this random variable here. It's this distance in this picture. But if the disk ends up over here, then x is some really teeny tiny number, right? X is over here. So this is x close to 1, close to 1. It's approximately halfway. And then this is like a teeny tiny x, okay? And the point is that x is random, and by doing it this way of measuring where inside one plank we are, we have turned x into a number that is definitely in the interval 0 to 2. So by its definition, x is somewhere between 0 and 2. It is either 0 would mean it's all the way up to one side, very close to this, and then 1 would be all the way on the other side. It's somewhere between 0 and 2. And the good assumption is that it is uniform, just like we talked about in class. So it is equally likely to be in any interval from 0, 2. So 0, 2 in closed brackets means this interval 0, 2, proportional to length. So this was just like, I think we called it U before, and it was the time of a light bulb. And we said the chance that it goes in the first half. So let's do an example. The probability that x is between, let's say, 0 and 1, that would be 1 divided by 2, because the total length is 2, and we're talking about an interval of length 1. If we said, what is the probability x is between 1 and 1.7, that would be 0.7 divided by 2. So whatever the length of some interval is, and you ask, is x there? It'll be proportional to the length of that interval. You have to divide by 2. That's the total length of the interval to make it an honest probability. OK, so now we're really cooking. That is, I swear to God, that is 95% of the work of the problem. It's drawing the picture, figuring it out, and figuring out that you should use this random variable x. The next thing we're going to have to do is turn the touching 2 points or touching 3 points into questions about x. When x is here, we're touching 3. When x is there, we're touching 2. Questions or comments about the setup so far? I think it will be instructive for you. Try to do this. This part is useful. And it's almost like a geometry problem. Like it's not really a super probability problem anymore, but it is geometry. So for what values of x is it touching 2? And for what values of x is it touching 3? OK, so let's write that down. For what values of x is it touching 2? For what values is it touching 3? OK, I'll let you think for like a minute or two. If you can come up with a good answer to this question, calculating the probability is a snap. The hard part now is doing this. OK, let me give you a timer here for a minute or two, and then we will take it up. See, anyone have a nice answer for either of these? I will remind you, these are sort of opposites. So you can do whichever is sort of easier, and then just find the probability of that, and then do 1 minus if you need to flip for the answer. I don't even remember what the question wanted to do. But you essentially get your choice of which one of these two you think is easier that you want to do. So you don't necessarily have to do both. Anyone have an answer for either one, 2 or 3? Yeah. Yes. OK, this is a great observation. If it's in the middle, 0.25. I totally agree with that. Oh, sorry. Did you say touching 3 or touching 2? Touching 3. OK, yeah, that makes sense. So kind of for it to touch both, it has to sort of be kind of near the middle. If it is too far over to one side, then it'll look like that. Or if it's too far over to the other one, it'll look like that. So the middle, 0.25, this is exactly where I would start. And then the question is, can we turn that into an interval? Like x is between something and something else. That is the question. If you can do that correctly, so first get this intuition of the middle 0.25 and then turn it into this, then you can figure that out. I suppose we don't actually need the exact interval. We just need its length. So maybe you could do a cheat and just say, hey, it's got to be 0.25 long, and then get the probability. So maybe you don't actually need the x values. You could skip a step. But let's just to be complete, to make sure we're sort of writing down everything we need to write down, let's actually get the actual endpoints. Did anybody get the actual endpoints? Yeah. 0.75 and 1.25. OK, so this is 1.25. OK, yes. OK, this is one thing. Is there's going to be some weird corner cases right at the edges. Why don't we get rid of the equals to? The nice thing is it doesn't super matter what happens, because for these kinds of random variables, remember the probability it's equal to any individual point is 0. So for example, the probability that x equals 1, that's 0. And so the probability that 0 is less than or equal to x is less than or equal to 1 is the same exact thing as the probability 0 is less than x is less than 1. It's all the same. So you don't need to be super careful for these ones about the equal signs like you do for the discrete ones, but it is good to get it right. OK, I will say this one to me makes it seem like the interval is length 0.25, and this one makes it seem like the interval is length 0.5. So you got to be careful when you do it which one's right, and that is why it's worth doing this extra step to make sure. The way I would draw it is I would redraw my picture bigger. Yeah, when I was in high school, I ran this math club. And one of the problem-solving tips I told all the students was, if you don't know what to do, draw a bigger picture. And then they were making fun of me all the time, drawing really big pictures. But it's legitimately a technique I use. And now I'm drawing a big picture. OK, so what is that? OK, I want this picture. So the middle line is supposed to be sort of the endpoints. So OK, so here's the 2 inches. This is zoomed in. 2 inches. And I guess the 2 endpoints are like this. Right? This is all the way to the left, and then you can have like a similar situation where it's all the way to the right. Okay, and then we care about the middle. So let's draw the middle of each. So the middle, and let's figure out what those are, right? So the middle of the big red circle, that's when the red circle is just barely touching the left. The middle of that will be one end, and then we'll do the same thing for the orange circle on the right. But let's figure out what this is supposed to be. So this entire distance from here to here is 2.25. And so where is the middle? Well, the middle should be 1.25 from this side. 1.25 from that side. Nope. There, I made a mistake. I was trying to do half of 2.25, right? So if the entire thing is 2.25 and it's touching over here, then this will be half of that, not 2.25. I think it will be 2 1/8, 2.125, or 1.125. So this is half. 1.125 equals half of the 2.25. So that's my way of doing it with picture. So I think I'm going to get a different answer than what was suggested, which is a good thing we double checked. Someone tell me if I'm doing it wrong. Maybe I did it wrong. Who had a picture like this? A few people. OK, great. So that one's 1.25 on that side. Let's figure out what this distance is. That'll be the other side, right? What is this distance? That'll be the other bound. So we know x has to be less than 1.125. That means you're further to the left. X is less than 1.125 means you're further to the left in the big red circle. And the big red circle is right on the boundary of touching 2. So that's what we want. And then the other side is going to be this little distance. How do we figure out this distance? Well, I would use the orange circle this time. And again, this is 1.125, also known as 1 plus 1/8. And then this entire distance we said is 2, right? On the bottom here, this entire distance is 2. So what is 2 minus 1 plus 1/8? I guess it's 7/8, which is some fraction. Let's write it as 7/8. I like fractions. 7/8. Okay. 1 and 1/8. Okay. 1 and 1/8 to 7/8, and there's my little geometry picture. I think for this problem, you have to do something like this. There is no way around. Some kind of find the question mark in the picture. You could have done it with more of a number line than I did. I like the big picture with the circles. But something like this is not avoidable. And this is the punchline. It has to be between 7/8 and 1 and 1/8. Any questions about that? How many people got something like that in when I gave you time to work on it? Okay, maybe I didn't give enough time. Maybe that was my fault. But yeah, that's what you got to do. Okay, and then so last but not least, the very last step, the probability that 7/8 is less than x is less than 1 and 1/8. Again, we know this is this kind of uniform thing where it's proportional to the length of the interval. So the length of the interval is 1 and 1/8 minus 7/8, which is going to be a quarter. And then we have to divide by the length of the total length of the interval, which is 2, or 2 minus 0 if you want, because x is between 0 and 2. You could have, like I said, you could have skipped some work if you had reasoned that this interval, regardless of what it is, has to be 0.25 wide. So that is a quarter over 2. And you could have maybe skipped the work of finding 7/8 to 1 and 1/8 by saying, I know that it has to be a quarter wide because of some reason. And I think that was kind of what was being suggested up here, which is a nice shortcut if you want to do it that way. And then finally, you get 1/8, which is the right answer. 1/8. So there's a 1/8 chance. It has to be pretty close to the middle to touch 3. And this kind of matches your intuition. If you're throwing it, it's like a very tiny bit wider than the planks, then of course there's a small chance that it will touch both. Okay, that's a full, complete solution to that one. Any questions or comments about that one? Yeah. Yes, that was the first thing I said. This is a little bit harder than would be on midterm. To me, this is like 2 problems baked in one. There's like this hard geometry problem, and then there's just like not too hard probability problem. If something like this was going to be on the midterm this year, we would tell you this, and then say, please find the probability. So it would just be like the last step. Yeah. What did I do at the end? Okay, so I'm using, I'm doing some stuff that I talked about earlier, so I did it a little bit quickly. So we figured out this, that x has to be between 7/8 and 1 and 1/8. So this is the event that it touches 3. It touches 3 is the same as it touches 3 only when x is between 7/8 and 1 and 1/8. So the probability it touches 3 is the same as this. And then here I use the formula that I mentioned before. For these uniform random variables, the probability x is in AB, some interval AB. A less than x less than b, or less than or equal to, or however you're going to do it. It's b minus a divided by the total length of the interval that x could be in. And so in this case, it's b minus a divided by 2, because x, we were told, is in 0, 1, or 0, 2, rather. 0 to 2. Okay, so that's the formula I use. This is the so-called uniform that we were talking about in class, I think on Friday, where we were saying there's a light bulb that will go off at some point in some time. What's the probability it goes off in the first half? Well, it's a half. What's the probability it goes off in a 1-second interval out of an hour? Well, it's the ratio of 1 second to 1 hour, this kind of stuff. Okay, yeah, great question. Anyone else for questions? Okay, alrighty. Let's see what else people wanted to cover. Okay. Okay, everything else has a 1. Let me see if there's any. 12 and 13. Okay, that was another vote for 13. No, okay, this person has a few. 13, 14. I guess, let me go by size of thing. Okay, so 13 we did. That was probably the biggest. What else is big? 25. Let's do 25. That one's standing out to me. That looks pretty big. Let's do 25. Okay. 25. Okay, great. So this is a discrete random variable. It's right there in the thing. So there's no continuous stuff, no finding areas. It's all about numbers. What is the hard part in this problem? You have to do a little bit of algebra, like really basic algebra with the x equals x. So a discrete random variable has its probability distribution specified by the function, blah. What is the probability? Absolute value of x equals 1. Okay. I have dropped the microphone. Is that what the kids say, drop the mic? That's what they mean these days? Probably not. Okay, let's move this one into our thing and work on it. Okay. Okay, once again, the hard part of this question is don't get bamboozled by the notation, right? The core things are not so hard, but there's all this notation you can really, if you're like, hey, what do I plug in to get the answer? Like, you will not get the answer. You have to think about this sort of, what do you know? What is given to you? What can you find out? This kind of stuff. So the first thing is, this thing is given to us in terms of x, and that's like annoying. Why don't I just make a list of all the probabilities? So let's convert this to something you're probably more familiar with, which is a table. Let's do this. So let's do, and what am I going to put in the table? So I have x values and I have p of x. What values should I put in my table? Well, they're given to me. Look, they were told over here. So I'm just going to make a table, -1, -2, 0, 1, 2. Very nice. And I'm going to calculate the p of x value. I think this will, like a lot of the reason this looks scary is because there's this like crazy formula and you're used to looking at tables. Let's just plug it in. So you plug in x equals -2, -2, x lowercase x equals -2. So x squared is 4. X squared is 4. So this will be 4 plus 1, also known as 5, divided by k. This one will be when x equals -1, x squared equals 1. So this will be 1 plus 1 divided by 2, 1 over k. 2 over k, rather, 1 plus 1. When x equals 0, x squared equals 0. And then you add 1. So you get 1 over k. And then it will continue the other way. When you square numbers, the positive or negative goes away. So I think this one will be 2 again, 2 over k and 5 over k. So that is the first step to make the question a lot easier. If you can go from there to there, now this might be a question that you recognize as being kind of very straightforward. Were there any questions or comments about what I did there? Again, this is like assuming you know how to read these kinds of things like x values and that kind of thing. That is a skill you need to build up for these math classes. Questions, comments? Okay, let's continue now. Oh no, I can't find any probabilities yet because it all depends on k. So the next thing you got to do, how to find k. How to find k. Okay, and to know how to find k, this is one we've done in class a few times. You need to remember one fact about random variables. If you use that one fact, you will get an equation, and then you solve that equation, you'll find k. But what is that one fact that you must use? Are you stretching or? Yeah, go ahead. They all add to 1, yes, exactly. So all probabilities all together, it must add to 1. So this is the fact. If you remember this key fact, then you will get an equation. The equation in this case is 5 over k plus 2 over k plus 1 over k plus 2 over k plus 10 over k equals 1. And don't replace the last 5 with the 10. Okay. There you go. That's the equation. If you tried to skip this table part and writing them out, you might have gotten a really nasty sum with x's, and then you would have gotten confused. So that's why it's helpful to write out the table. Okay, what is this sum? You really got to do it. 5 plus 5 is 10. 2 plus 2 is 4. 1 is another 1. So I think I got 15. 15 over k equals 1. And if 15 over k equals 1, then k equals 15. K equals 15. Nice question. Or nice conclusion. So if k equals 15, now I know all the probabilities. Before they were given in terms of this unknown k, but now I know k equals 15, so I can write them all down explicitly. All right, there's one more part of this question that is potentially confusing, is the probability. And then they wrote these weird vertical bars, x equals 1, these weird vertical bars. And I did not have weird vertical bars on my bingo card here. So like, what does that mean? And I think you got to turn this into you got to convert this, again, by means of understanding what the probability that x equals blank or x equals blank, or like, what values could it actually be? X equals blank. Like turn it into an actual honest to God list of values for x. Get rid of the weird vertical bars, and then you will understand. The weird vertical bars are the absolute value function. How does one understand the absolute value function? I like to draw a graph. Let's do. This is the absolute value of x. Y equals the absolute value of x. And so when someone says the absolute value of x equals 1, they're saying the y value on this graph is crossing y equals 1. What are the two x values? There's two of them. There's one here and one there. Where it crosses, it's x equals plus 1, but also x equals minus 1. Okay, so based on this picture, I'm going to figure out for which x values is the absolute value of x equal to 1, and then I'm going to use that over here. But let me slow down for a second and pause. Maybe if you're less familiar with the absolute value function, this is kind of an annoying problem. Questions or comments here? Okay, so let's, based on my picture, the point is that there are only two possible values of x that will work to give an absolute value of 1. There's x equals plus 1 and x equals minus 1, plus 1, or x equals minus 1. Those are the two things that can happen. In this situation, you can add them together because it can't be both at the same time, so these are disjoint. We can use our plus rule. Okay, and so it's either plus 1 or minus 1, add them together, and now I just got to read it off my table. My table says plus 1 is 2 over k, and minus 1 is also 2 over k. So it's a 2 over k plus 2 over k, also known as 4 over k, and because k was 15, it's 4 over 15. That is what I got. Questions about that one? This one, I guess this is like really a 1,000 cuts problem. There's a few different small things. There's no one big idea. There's like a bunch of small ideas repeated. Make the table by plugging in this trick on finding k value, this trick on unpacking something into its individual values, this trick on adding. You got to combine all the tricks. Okay, let's do another one. Unless there's a question. And we will choose based on font size. Okay, what's the biggest one? We did 13, we did 25. Q12 maybe is bigger. Let's do Q12. Q12. Let's try 12. 12 from the practice problems. Okay. Ooh, great. Okay, this is a good one. Oh, this is again. I'm in the answers. Let's get out of the answers. 12. Yeah, there was a mathematized homework question that was exactly like this problem. So if you nailed that one, or you reviewed it, you will have no problem with this one. Okay. 10% of horses in the province of Ontario have a certain type of internal parasite that requires surgery to detect. Horses are sampled at random and checked for the parasite. What is the probability that more than 6 horses will need to be checked to find the first with this type of parasite? So we want, at the end of the day, we want the probability that there is more than 6 horses needed. So we're going to check until we find one. To me, this one, I would draw this kind of probability tree to figure it out. So there's the first horse. We're going to check if it's there or not. And then the second horse, and so on. And we're going to get some kind of picture like this, where it's going to go all the way up to 6. Dot, 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 all the way up to the 6th. Sixth horse. So I skipped the horses 4 and 5 there. And then I just got to figure out what exactly I'm doing. So I want the event we're asking about is that there's more than 6 horses needed. So the thing I care about maybe at the end is that we haven't found the parasite yet. So we haven't found it yet. Maybe this will be the sort of end point over here. We haven't found it yet. And so if we make it all the way down the tree and we get to we haven't found it yet, then that'll be the probability we're looking for, that more than 6 horses are needed. If we tried 6 and we haven't found it yet, that means we need more than 6. So it's going to be that endpoint on the tree. These other ones will be like, we found it after 6 horses. The found at 6. Found at 6. And this one will be found at 3. And this one will be found at 2. And this one will be found at 1. Okay, and if I have these things, then I can label what the branches are supposed to be. This one will be it's found, and this one will be it's not found. And then I can read off from the question which one is found and not found. 10% of horses what? They have. 10% of horses have it. So this will be a 10%, and then that one will be a 90%. So let's label that. Let's do orange. 10% chance to find it, and a 90% chance to not find it. So 10% chance we find it right away, then a 90% chance we don't find it, and then we have to try again. And then so that level will be another 10% branch, a 90% branch, a 10% branch, a 90% branch, all the way up to a 90% branch, and a 10% branch. Okay, so there you go. What do we want to know? We haven't found it yet after 6. It's just this main spine 90, 90, 90, 90, 6 times. So the probability is 0.9 to the power 6 by the tree. Okay, that's how I would do this problem. Is that one of the options? That's option A. I was spoiled because I opened the wrong file. I think the answer was option A. Okay, that's how I would do it. You might say, what is this doing on a test that's mostly about random variables? Where are the random variables here? Does anyone see where the random variable is? This problem is actually, we did it without random variables, but you could have also said there's a random variable. Yeah. You're very close. You can use the blank distribution, but the word blank is unfortunately not binomial. It's the other one. Does anyone know the name? The blank distribution. I hear some whispers. Someone's saying it. Maybe you guys. What did you whisper? Now you have to tell us. Geometric, yes. So you could also do the geometric distribution. And this picture that we drew is actually our derivation of the geometric distribution. So if you draw the same picture again, and you say found at 1, instead you say x equals 1, and then you say, no, if it's not equal to 1, then x equals 2. So you replace the found at 1, found at 2 with x equals 3, ... And then your last branch will have x equals 6. And what will we replace we haven't found it yet with? We'll replace it with the event that x is bigger than 6. So in other words, if you let x equal the number of horses needed, this is a geometric, and I believe it's a geometric 0.1. So you got to remember what the parameter means. It's a 0.1 because each of these branches is 10%, and each of these is 90%. And so if you had this on your crib sheet, you would be able to figure out that the probability for a geometric, the probability that x is bigger than 6 for a geometric, it is, I believe, 1 minus p to the power 6, which is 90.9 to the power 6, which is what we had. So you could have, if you had recognized it as a geometric and used that information, you would have found it maybe a little faster. You could do it either way, of course. Yeah. Yeah, tell me about a binomial. I think it's not a binomial, but you tell me why you think. Ah, okay. You have absolutely convinced me you can do this problem as a binomial problem. Let's do it that way. So let me do it as a binomial. The way I did it was as a geometric. You can have a different way of doing it as a binomial. So let's let y, let's call it n. So, okay. Let's call it n. N stands for the number of horses that have parasites. Number of the first 6 horses. The first 6 horses that have parasites. So the way I did it was as a geometric variable, and I said x is the number of horses we need until we find one that has the parasite. So this is quite different than the setup over here. X, you notice there's no 6 or anything like that, right? X is the number of horses we need. We're going to keep getting horses. We're going to go to the horse garden and pick a new horse until we get a horse that has a parasite. We're going to keep going and going and going. And then I had this nice picture. And then it was a geometric. So X was geometric. If you want to do it a different way, and you want to specifically answer the question over here, you can say N is the number of the first 6 horses that have parasites. And then the event that we need more than 6, that becomes the event that N equals 0, right? So this is in contrast to what I did. What I did was the X equals 6, X greater than 6, right? So we need more than 6. We need more than 6. That was the event that X is bigger than 6. And so if you want to write it in terms of X, it's kind of like more intuitive. But you can do this tricky thing and say, if in the first 6 horses, none of them have parasites, then we need more than 6. Absolutely correct. And then you can say, OK, well, the probability of that, the probability of we need more than 6, that is the probability that N equals 0. And N, you recognize N is binomial. Binomial with 6 and 0.1. And then you can write down the probability that a binomial is 0. For a binomial to be 0, all 6 horses have to work out to no parasite. So no parasite. No parasite 6 times. So if you want 0.9 to the power 6, 0.1 to the power 0, and then you're going to have a 6 choose 0, I guess, if you're using your sheet. 6 choose 0 is 1. 0.9 to the power 6 is what it is, and 0.1 to the 0 is also 1. So you get the same answer as before using a binomial rather than a geometric. I personally think the geometric is more intuitive for this problem. Of course, this is also perfectly fine. So yes, a good alternate solution. Yeah, great question. Yeah, question here. How do you know which one you're supposed to use? I think the way I think you should see maybe all of university math is we're telling you a bunch of tools, and you can use the tools to solve various problems. In this particular case, both of them worked. I'm trying to think of, in some situations, like literally only the binomial will work. That's pretty common. If there's ever, if we say like, we tried so many trials, what's the chance that exactly 3 of them came up, right? Some question like that. Or, there's 20 things, how many, what's the chance that there are 3? Like if it was somewhere in the middle and it wasn't exactly N equals 0, if it was like, what's the probability 2 of them have parasites, then it would have been really like very strictly binomial. And it would have been quite hard to get it the other way. So the answer of like which one you should use when is like I think you should know both, and you should be able to apply them and recognize when to apply them. I don't think there's like a one-line slam dunk. When it's like this, do this. Unfortunately, yeah. Great question though. Anyone else? Okay. Do we have time for one more? Maybe we have time for one more if it's a very, very short one. Let's get in there and see what people said. Okay, I don't know. Let me just let's do one of these. There's some of these tricky multiple choicey ones where you don't really have to do a lot of calculation. You just have to like think about it in a right way. Here's a good one. This is one we did in class about why is this thing true that when you take a test for a disease, even if you get a positive test, it doesn't mean that the probability you have it is somewhat low. So the reason the probability is low when we consider a large population, and then there's all sorts of different combinations of true and false positives. And I think we got to remember, let me just write down how I would think about it. The reason the probability is low is because people who actually, the probability is something like people who actually have the disease, people who actually have disease divided by people who test positive. That is the number that we're talking about being very small. And the people who test positive, that can be further subdivided into 2 groups. So the people who test positive is people who actually have it and people who test positive but don't have it. This is the sum of people who have it, people who have it, plus people who don't have it but test positive. People who don't have it, but test positive. Okay, and the people who don't have it and test positive, is what we call false positives. So it's wrong because they don't have it. That's the false, and they test positive. So that's a false positive. So the false positives have to outnumber somebody, and who do they have to outnumber? These are the true positives, the people who actually have it. Okay. Oh, or maybe more accurately, those people. So the false positives are much, much larger than the true positives. That's why this fraction is very small. So that would be, if I can find the thing. Okay. The false positives are greatly outnumbered by the false negatives. No, that's not what I want. I want true positives are greatly outnumbered by false positives. That's option A as well. Okay. Oh, that was very quick. I think there's another one like that. Oh, yeah, this one. This is the one I wanted to get to. The continuous random variable x has a probability density function f. For any value of a, which one of the following statements is false? Some of these ones we've already done today. I mentioned this one about the less than a and the less than or equal to a. Those are the same. The greater than or equal to a and the greater than a. Those are both definitely true. We mentioned those, and those are true. These ones, these are the flipperonis that I was talking about, where you can flip an x greater than a into 1 minus the x is less than a. Very technically, you would flip it into x is less than or equal to a, but of course, less than a and less than or equal to a are the same. So the last one, option E, is definitely true. Option D is sort of tricky, but also technically true. What does that leave us with? Wait, which one of these is false? This doesn't look wrong, though. The probability x equals a is f of a. That sounds right. It's got a nice ring in my brain. The probability equals the function, right? But there's a mistake. Who can tell me what the mistake is? Why is A actually false? Yeah. The probability is 0 at any point. So the f function, remember, gives you the height of the graph you're finding the area under. So the height is the function f, and the area is the probability. So the probability x equals A is the area underneath a point. But because it's infinitely thin, that area will be 0. So option A is wrong. It should say the probability of x equals A will be 0. The height of the graph is f of A, not the probability. So there you go. That's another one where the answer was A. That's funny. Okay. All right, I'll be here for a few minutes if you want to chat or have any more questions. But otherwise, see everyone tonight at 7 p.m. And good luck. Make sure you bring in your crib sheet.